So in the next 1 hour, we will look into some collection of ideas, but they are interesting, but we didn't get enough time to study them in this course. The first observation is this, okay, that when we worked on this dense matrix vector multiplication or dense matrix multiplication problems, these BLAST problems, an important thing about them is what do I say? They are there is a lot of regularity in the memory accesses. There is a regularity in the computation, and the parallelism structure in the program is available for analysis. We can have automated compiler analysis techniques which can kind of analyze this program and say, hey, this is the dependency structure of this program. And based on that, we can do some kind of parallelization. Okay, the compiler can do auto parallelization or we can do manual parallelization. But then these are all regular memory accesses, regular computations. But in many applications, so we may not have that kind of regular memory accesses or regular computational structures. We are working with arrays all the time when we are working on BLAST problems. So in many scientific applications, we see what are called as sparse matrix vector problems. The matrix may have large number of zeros and few non-zero entries. Similarly, a vector can have large number of zeros and few non-zero entries. So, and just representing the whole matrix in the regular form is waste of memory. Okay, maybe let's say if 20% of the entries are non-zero and the 80% of them are zeros, then using an array to represent them itself is a waste of memory. So there are alternate representations for these sparse matrices and sparse vectors. And when there are alternate representations, like for example, if only 20% of entries in a row are non-zero, then we don't want to store the whole thing. Instead, we may want to store something like row 1, column 2, this is the value or something like that. You can kind of think of an adjacency linked list, the way you represent graphs, etc. Adjacency representation of graphs. Or there are many standard formats that are available. And the algorithms also change. Right now we are writing for ijk or for jki, whatever different ways of writing our loops. Then we have to, the way we write algorithms for the sparse matrix vector problems, it will also be different. And the parallelization strategies will be different. And there is a special set of benchmark programs called as sparse BLAST problems. Like for example, like while we have, what do you say? This is, so if GEM is the generalized matrix multiplication, then we have SP-GEM, which indicates we are working with a sparse version of this problem. Okay. Needless to say, there is a lot of research on this problem, the sparse problems. They are more challenging than the dense problems. And the kind of gigaflops that you can achieve, gigaflops per second that you can achieve for the dense problems, you will not be able to achieve on the sparse problems. And so even for GPUs also, when you are working with GPUs, GPUs can give fantastic numbers on dense BLAST problems, but on sparse, they also have the limitations, and there's again a lot of research on this space. The second set is irregular data structures. It's not that the case that we all the time work with matrices, and you may be working with, depending upon, you might be working with graphs, you might be working with trees. So if you think of a tree, uh, um, then so simple binary search tree, the memory access patterns are all over the heap. You access a node, you check something is less than or equal to, you go to a different node, and then, so the memory access patterns are all over the, all over the heap. And so the effective memory bandwidth that you get is so low, and there's quite a, it's challenging to design algorithms, data structures which are memory efficient or cache efficient, which can use the cache locality property. So, okay. In the binary search, yeah, yeah, that's true. Well, that is true. So that's what can happen is, in a binary search node, let's say if this is the search routine that you have, so typically when you do, let's say there is something, C node is the current, you may be doing something like C node key greater than whatever that whatever the current key that you are checking, and depending upon that you may want to go to left or right. So you can explicitly, one way of handling this is explicitly inserting prefetch instructions. These are software prefetch instructions. You can prefetch both left and right, and yeah, so yeah, it has challenges because if you prefetch both, and you discard one, so that's going to be a challenge. But if you are, let's say, if you're traversing a linked list, which is more predictable, let's say if you're doing a linear search on a linked list, when you are doing a comparison on the current node, you can issue a prefetch instruction to the next node. Okay. So that kind of, so you have to, it's not easy. Okay. So inserting prefetches, the compiler automatically does it. If you do aggressive prefetching, it may kind of eject the currently active data. And if your prefetching is not, if it is too late, you still end up paying memory penalty. So how do you insert the prefetch instructions so that you are not too aggressive and you are not too delayed? So challenges there. So did you study in your data structures course B trees? Or are you studying B trees in any other course now? B trees are secondary storage or indexing structures for hard disk, where in a node, instead of storing only one key, we store a bunch of keys. And uh, yeah, so you can think of, at least in 2-3 trees or in AVL trees you studied, right? So in AVL trees or 2-3 trees, you have at least 2 or 3 keys per node. So in B trees, what happens is a node kind of nicely, it's primarily designed keeping in mind hard disk. So a node nicely fits into a sector of the hard disk. Because when you fetch a hard disk, you have to fetch the whole sector. So if you are just accessing only one element in the hard disk sector and trying to get one more element, it's going to be very expensive proposition. So they kind of pack it so that each node nicely fits into a sector. And when you study databases, a whole, yeah, so I guess you will study quite a bit about this. But anyway, the point there is, the B tree structure is optimized so that you reduce the number of disk seeks. And when you lift up that logic to L3 cache to main memory, you can apply a similar kind of strategy, except that in the L3 cache level, we don't have control on, no, it's all transparent. We don't know the block size and lots of other things come into picture. Okay. Well, in this context, I want you to study. I will not be teaching you, we will not be discussing that. I would like to look at what are called as Van-MD Bose trees, which are supposedly Van-MD Bose trees. I will not, these are what are called as cache oblivious data structures. Van-MD Bose trees. Okay, so this is what is called as a cache oblivious data structure, because the nice property of this tree structure is you don't need to know the underlying structure of the cache, but the particular way in which keys are laid out in the memory, they automatically use the cache. But of course, there are challenges in using this tree. But nevertheless, you should take a look at this and understand that way the keys are laid out in the memory and why that laying out of keys in the memory is beneficial for it's good for utilizing the caches, all the levels of caches well. Okay. So again, as I said, this all, whatever I talk in the next 1 hour, I will not get into details. I'll throw some key terms and yeah. So, and I would like you to look up into that. And so in this here, the best place to look at this is in order to understand Van-MD Bose trees in MIT in advanced data structures course. You should look at it. Okay. So it's a superb lecture. It's very, all things are properly discussed. So that's the reference. Okay. What else? Now I will switch gears and yeah. So we will look at let's see. On this. So we will look at one interesting parallel, one kind of problems where you see all the theory that we have, the strategies that we have thought, we have learned, they don't quite pan out well. Okay. So this idea called as amorphous data parallelism, and a lot of work related to this space has come from Professor Keshav Pingali's group in UT Austin. So this work is done around 2010, 2012, but the ideas are still relevant, very important. And a lot of current research on domain-specific languages, graph DSLs, is based on the work from this group. So the problem here is, we'll just take an example problem and try to see what's going on there. Then we'll see, what comes out. So here there's this problem of triangulation. So there's a polygon that is given to us. We have to triangulate the polygon, and the constraints in triangulating the polygon is if there are two triangles adjacent to each other, their entire edge should be common. For example, here, this is not a good triangulation, because this edge of this triangle shares this edge with two other triangles, so it's not a good triangulation. Okay, so if two triangles are sharing an edge, it has to be complete. And then triangulation of a set of points is, given a set of points, we compute a convex hull of those points, and we would like to triangulate that convex hull. And there is what is called as a Delaunay triangulation. In Delaunay triangulation, if you take a triangle and when we draw a circumcircle for it, it should not include any other vertices. Like, for example, if you take this triangle and the circumcircle for this, It doesn't include any other vertices, so it's a good triangle. But if you draw it, so if this one contains, maybe if there is something like this, then this is a bad triangle, because when we draw the circumcircle, it included this extra point within, so it's a bad triangulation. Okay, so it's a bad triangle, and then so we want to retriangulate it so that this property is satisfied. Okay. Yeah, so this is what you are seeing here on the left here in figure 1. It has a bunch of bad triangles. So bad triangles could be, the angle is less, or the circumference property that we have talked about. So what we do is, whenever we identify a bad triangle, so we identify its neighborhood and retriangulate the whole region. So like, for example, this whole region is retriangulated here. Okay, so this got transformed into this. So the problem in this, so if you take this one, if you write an algorithm for this, so you have what is called as an initial Delaunay to start with, and there is a list of bad triangles. You pick a bad triangle and you pick the neighborhood, and we call the neighborhood of a bad triangle cavity, and we retriangulate the whole cavity associated with a bad triangle, and then we move on to another bad triangle and we continue this process. The problem in this approach is, if you see, if you write code for this, the compiler can no way figure out a strategy for parallelizing this code. Because if you see, if there are what is the parallelism that is available here? If there are two bad triangles, and if the cavities associated with those bad triangles, if they don't overlap with each other, then they can be retriangulated in parallel. Yes or no? That's the thing. But the problem is, until you do this thing, it's not possible for us to figure out whether these neighborhoods, the cavities overlap or not. So if you take this problem and if you just give it to compiler, Intel ICC compiler, Clang, or any compiler will not be able to parallelize this code, because the structure of the parallelism is not available at all at the compilation time. The structure of the parallelism keeps on evolving as the problem keeps moving from one stage to another stage. Okay, and this is what is called as an amorphous data parallelism. And so here, so we have to come up with alternate strategies to kind of work with this kind of problems. So that's where new programming language constructs we can come up with. Like, for example, you can have a work list of bad triangles, and then you express the computation like it. For every bad triangle in this bad triangle set, do this refinement. If you can express this computation like this, then what happens is the compiler, what it will do is, it will schedule these computations B1 of, let's say on your machine, you have 4 processors, P1, P2, P3, P4. So like B1E, B2E, B3, B3, B4, or actually that's not the right way to do it. So it can say, you process at G1 or bad triangle E1, E2, E3, E4, it can schedule them. Okay. So when the compiler, and then maybe, so this may take some time, and then it can schedule B of E5, and then it can schedule B of E6, so on and so forth. The compiler can schedule the work that is present in this work list. And during the process of retriangulation, you may end up adding more bad triangles, and those bad triangles should be added back to this set. Okay. So now, what are the challenges here? Do you see any problem in this approach for parallelization? There's a construct, there's a programming language construct which lays out the structure, underlying structure of computation. But are there any challenges in this approach? The challenge here is if the cavity of E1 and E2, if they overlap with each other, then this is a problem. Yes or no? Then what happens is the compiler or the runtime system, not the compiler, the runtime system may have to abort the computation of B of E2 when it sees that there is a overlap happening between them, and no, and then reschedule it B of E2 later. Okay. So if you study later, maybe databases, there is this idea of linearizability. Okay. The idea of linearizability is when there are multiple computations happening, the result that we get, it can vary depending upon the order in which different things are scheduled. But what we get finally, it should be equivalent to some linear schedule of computations. Does this make sense? Like for example, the initial mesh state is M. Okay, the initial state of the Delaney mesh is M. If you schedule the computations that are there in this set in some permutation pi, in using some permutation pi1, you may get some final mesh M of pi1. And if you use different permutation pi2, you may get a different permutation M of pi2, so on and so forth. So we don't care which of the final outcomes we get, as long as the final mesh that we get is equivalent to some permutation. Okay. So when the runtime system is scheduling these computations that are parallelly scheduled, the net effect should be the net effect of scheduling these computations in parallel. It has to be equivalent to one of these permutations. And if that is the case, then we say that this parallel schedule that we have is what is called as a linearizable schedule. Linearizable schedule. Are you with me? So in order to build a runtime system for this, to solve this problem, there are quite a bit of challenges that we have to face, because solving this linearizability problem is non-trivial. Okay. Did you do any databases course so far? Okay, okay. So acid properties in operating systems course, did you study acid properties? Not in operating systems. So when you have these file systems, like when multiple operations are happening in the file system, multiple threads are working on the file system. So one thread could be doing insert, another thread could be doing delete, another thread could be doing modify. So the net effect on the file system should be equivalent to some ordering of the operations. It cannot be like, the state that the file system moves from one to another, when multiple threads are acting on the file system, it should be equivalent to some permutation of operations. If that's not the case, then the file system is in a bad state. Okay. Does this make sense in the context of file systems? Similarly here, there is original data structure that is a Delaney mesh that is there. We are applying a sequence of operations on this original data structure. The net effect on the data structure, it should be like that. It should be equivalent to some sequence of operations, as if thread T1 acted and then thread T2 acted and then thread T3 acted, so on and so forth. And that also brings to a whole area of research which we are not talking about at all, which is concurrent data structures. So in the concurrent data structures, so in this course, we didn't study anything about concurrent data structures. But if you are designing an AVL tree, okay, so if you are designing an AVL tree and you want to come up with a multi-threaded version of the AVL tree. So when you are doing an insert operation in the AVL tree, perhaps you may want to balance the tree because the height mismatch happened or something like that. So while one thread is trying to do the balancing operation, another thread comes and do some delete or something like that. And what will happen? Things could go back. go bad, right? Yes or no? So what is the easiest way to solve that problem? Yeah, you log the whole data structure. You take a fat lock on the whole data structure, then for all practical purposes, it's a serial data structure. No? So how do you refine this lock? Or there are strategies how there are what are called as lock-free data structures also. Okay. That's again a whole area of research where how we can come up with data structures where multiple threads can act on it. Again, the semantics of that, when we are designing these multi-threaded concurrent data structures, when multiple threads are acting on this data structure, the net state in which the data structure land up in is equivalent to some order of insertion, deletion, search, etc. Yes or no? That is called as, then we say that the concurrent data structure that we have come up with is a linearizable data structure. Okay, it is equivalent to some linear ordering. The execution is happening concurrently, but in terms of semantics, we are giving what is called as a linearizable semantics. So this linearizable semantics is very, very important, because in the absence of that, it's very difficult to wrap around and understand when we give a search operation on a data structure. What does it mean if it says if the key is present versus if it says if the key is not present? But if it's the data structure is linearizable, we can say, hey, these operations happen, and then the search happened here. Because of that, the search gave either the key is present in the data structure or is not present in the data structure. Okay, so that is the linearizability. Okay, so yeah, so here in this context, okay, so these are the things I would like you to keep in mind. One is so far what we have looked at is number one, sparse blast problems. Number two is when we are designing irregular data structures, there are what are in order to use cache as well, you can either you can use prefetch instructions, which are difficult to use, or we have what are called as cache oblivious data structures, which are VanMD is an example of a cache oblivious data structure. Number two. Number three is there is this idea of amorphous data parallelism, where the structure of the parallelism evolves, and so we have to use some language constructs in order to expose this dynamic parallelism that is there in the system, in the algorithm, and the runtime system has to use this framework provided by the compiler, to somehow schedule the computations in a parallel way. And when it schedules the computations in a parallel way, some semantics needs to be respected. One possible semantics, one important semantics that we usually keep in mind is linearizability. And this idea of linearizability also carries over to concurrent data structures. Okay, I'm sorry for all the hand waving. That's last session is supposed to be hand waving. So now let's look at great. So we have this, now we are switching gears. We want to do a little bit of how we do what is called as a cache oblivious matrix multiplication. We'll go super fast, but let's hope we get something out of this discussion. So if you look at memory hierarchy, we have L1 cache, L2 cache, L3 cache, and main memory. For the sake of simplicity, just assume there is a cache. We are just working with L3 cache, and then there is memory, and then there is processor. And the cache is divided into blocks. Usually the size of this block is 64 bytes or 128 bytes or something like that. And so when when you're accessing, let's say this particular a byte which is present in this block, and if this byte is not present in this cache, if this is not present in the cache, the whole line will be promoted to the cache. Okay, so this is the Okay, so there you are accessing some element here, and if it's not present in this cache, the whole thing will be moved here. Okay. And the size of the cache is m bytes. And the size of each cache line is b bytes. And we are assuming fully associative cache. So what is fully associative cache? Do you recall what is a fully associative cache? Yes. So this main memory block, it can go anywhere in the cache. Okay, this main, that is direct cache, direct map to cache. Are fully associative caches used in practice? They are not used in practice because the time whenever you do a memory access, in order to search if it is present in the cache or not at a hardware level, it requires a lot of time and chip area also. Because of that, fully associative caches are not used in practice. But for the sake of simplicity in this analysis, we are just assuming that we have a fully associative cache. Okay. And what is the optimal cache replacement policy? What is the optimal cache replacement policy? Sorry? I think it depends. I think these LRU is the best. It depends on the problem. Optimal strategy. Farthest in the future, the one which you are going to use farthest in the future is what you want to evict. But you cannot find out, you cannot look into the future, so we approximate it by looking into the past. The approximation is evict the least recently used. And what is the theoretical guarantee that we get? It is within 2 times. If using the optimal farthest in the future cache replacement policy, if you get 100 cache misses, if you use LRU policy, it is guaranteed that the number of misses cannot go beyond 200. That is a factor of 2 guarantee is given. But LRU is, you can implement it. Okay. Actually, LRU in its purest form, implementing it in the hardware is difficult. So there are approximations of LRU that are used actually. Okay. Anyway, so that is about this. So now, yeah. So now let's consider matrix multiplication problem. What's the problem? Okay. So now we have the matrix multiplication problem. If you do a cache analysis, okay, so we are multiplying, so this dimension is n, okay, this dimension we are multiplying 2 square matrices. And the case 1 is this n, the number of rows is greater than m over b. What is m over b? M over b is the number of cache lines. M is the total cache size. B is the block size. M over b is the number of cache lines. So what happens here when, as we keep, when we access, we take the first row and multiply it against dot product with the first column, and then you compute the dot product with the second column, so on and so forth. So what's the analysis here? Okay, let's see here. So to compute each element of the product matrix, we scan a row of matrix A. When we scan a row of matrix A, how many cache misses we incur? So when we go through this, we incur n over b cache misses. Why n over b cache misses? Because when you access the first element, you bring the next chunk of b elements also. Does this make sense? So the number of cache misses incurred by the row scan is n over b cache misses. Okay. And then when we take the column and when we, so how many cache misses we incur when we scan the column? So everything is a miss. There are n cache misses. Okay. So overall, if you see, overall cache misses per product element is n over b by plus n, because you add these two things up, you get this. And we are computing n square such elements. So the total number of cache misses is n square times this. Okay. And why it is the case? Because when you try to access the next column, since n is greater than the number of available cache lines, by the time you come here, these elements, this cache line is already evicted. Does this make sense, right? Because this is one cache line, this is another cache line, this is another cache line. But what happens is by the time you go down, these first cache lines are already evicted. And they are least recently used. Okay, they are naturally evicted. So because of that, you end up evicting them. So every time that you access an element, you end up paying columns of B. Every element access will result in a miss. Okay, so this has super poor locality property. Almost all the time you are visiting the memory. So that explains, if you take a simple for ijk loop and see the gigaflops that you get, usually it is extremely slow because your cache utilization is very, very bad. Are you all with me here? Okay. So, and then there's a second important thing here. This row you are using, you take the dot product of this row with all these columns. There is a temporal locality with respect to this row. But again, the problem is, this row is evicted by the time you rescan it from the beginning again, because the size of the cache is too small to hold this row. Okay, so this is the challenge. Okay, so this is so these are the problems associated when the size of when the number of columns when n is greater than the number of available cache lines in the program. Sorry, number of cache lines in the processor. So now let's assume that the number of that n is less than that is the number of rows is less than the number of cache lines by some fraction. Okay, that means possibly the whole row can sit into the cache. Are you with me here? This is the second analysis that we are making. So in this case, so again, let's look here. This is so how many, when you are multiplying this row with this column, if you see cache misses due to row scans, n by b for the first scan and no misses for the later scans. Because you are taking this row and you are taking dot product with all these columns, but since this row can sit into the cache, so in the next subsequent accesses, you don't need to go to the main memory. So then, so we have only n over b cache misses. Makes sense, right? And now when we look at the column scans, so since again, what happens is for every B columns, when you go down here and when we go and try to access the next column would already be present in the cache because this block is not evicted. Okay, so that means if there are overall n columns, then the number of cache misses that we get is for every n misses for every B columns. Okay, does this make sense? For every B columns, and there are n by b such columns. So overall, what we have is n by b into B columns into B, which is n squared. If you, let's make it a bit more clear. If you draw this picture, so this is the first. Why it is not working? Okay. So does this, I just want to make it clear, and before I move on. So this is the first B columns. How many cache misses are incurred for the first B columns? N misses, right? Because for when you access the first row, one miss, second row, one miss, third row, one miss, so on and so forth. So for the first B columns, we incur N misses. And how many such blocks are there? N over B blocks. So N over B into N, which is N square by B. Okay, so overall number of misses is N square by B. Okay, so now, so put together this term and this term put together, this is the total number of cache misses. Okay, while computing one row of the while computing one row of the product matrix, this is what we get. And overall, there are n rows, so the number of misses is theta of n cube by. So how much saving we got from the previous? By factor of b, because earlier it is n cube, now it is n cube by b. So if the cache line size b is equal to 64 or 128, then that means the number of misses go down substantially by 64 or by 128, which is a very good save. That means the amount of main memory traffic got reduced corresponding. Okay. So now what we do is, this is n cube. Yeah, so now that the third analysis is, what if the cache is large enough to hold the whole matrix? Okay, how many misses are required to bring matrix A into cache? There are n squared by b accesses. No, every row you can get it in n by b accesses, and there are n such rows, n squared by b accesses. So you can bring the whole row, whole matrix A to cache, similarly bring it using theta of n squared. So the story is, if the two matrices nicely fit into the cache, then what happens is from n cube by b, you go to n squared by b, which is extremely good. Okay, which is extremely good. Okay. So with this as the intuition, we will not get into the details. We do what is called as a tiled matrix multiplication. And what we do is, we do this tiled matrix multiplication. When we try to choose the size of this tile, we choose the size of this tile so that the size of this matrix nicely fits into the cache. Okay. So you take this submatrix and then you multiply it with the submatrix of the other matrix B, and when you multiply them, what happens is that tiled the number of main memory accesses goes down. Okay, and so this code, you can see this tiled matrix multiplication. You can see it's a 6-way nested loop. Okay. The innermost three loops are for multiplication of one tile with another tile. Okay. And if you do the work analysis, during this process of tiling, we are not increasing the overall work that we are doing. The number of computations is still n cube. Okay. We will not get into the details, but if you do the analysis for this one, the overall number of cache misses in this tiled matrix multiplication, it turns out it will come to this. So from n cube, we will be able to reduce the number of cache misses by this factor. Okay, instead of n cube by b, we have b into square root of m. Remember, m is quite big. M is the size of the cache. So that means in the denominator, we have a huge value. So the number of cache misses will substantially go down. And because of that, we get very good performance. Okay. So now this idea of auto tuning, this size of the tile we don't know. Okay, the size of the tile, you can write a parametric code with S as a tile size, and you can write a program which tries no S is equal to 128, and what is the performance that you are getting. You try S is equal to 64, and if you get a better performance, you go to 64, and otherwise no, you go to 256, and you have to do some kind of search so that you get really good performance. The tile size depends upon the cache hierarchy. Okay, and the Atlas, the Atlas is a realization of these BLAS kernels, and what Atlas does is it has a parametric implementation of all the problems. And when you install Atlas on your machine, it searches for these parameters, which gives you the best performance. Okay, and fixates on. So there, usually when we talk about portability of all problems, we talk only about that problem should be able to run, the program should be able to run on the other machine. But there is this idea of performance portability. That is a code that is optimized for one architecture. If you run the same code on a different machine, will it give a performance which matches the gigaflops achievable on a particular machine? Okay, that's called as performance portability. In order to do performance portability, so we use these auto tuning techniques. Okay, and when it comes to auto tuning, there are three approaches. Okay, so we are talking now about auto tuning. So first one is the first one actually is why should you even do all these things? Can't we have a mathematical model which where we know, the cache size is in this on this machine is equal to m, the block size is this, then automatically the size of s should be something like this. That kind of analysis, we can have an analytical model to decide this analytical model to decide these parameters. That is one. But when we try to arrive at an analytical model, there are two problems there. What are the problems in arriving at an analytical model? Yeah, there are all external factors we disregard, we don't consider. And if we model all of them, no, we get a system which is not solvable, useless. But we have something to say, sure. Non-uniform memory accesses and Intel's cache, you don't know about Intel's cache. Intel doesn't give you all the details. Okay, you look at the manual, it has some stuff, but you may not get to know all the details about the cache architecture and those challenges. The second one is heuristic search. Heuristic search. Did you read an AA course, right? Yeah. Yeah, in AA course, you have all these A star algorithms and different search algorithms. No? So you can use any of those algorithms to find out what is the best parameters. Okay. The third, of course, is with all the latest stuff, you can use some kind of machine learning models to predict these tile sizes, etc. Okay. Let's. Not really. It depends on caches and all. Not really. And the story doesn't end here. The styling doesn't end here. You can see right now we modeled L3 cache with main memory, but there is an interface of L3 cache with L2. So what happens is you may want to do tiling within tiling. So when we do tiling within tiling, instead of a 6-way nested loop, you will get a 9-way nested loop. Okay. And it's not just L3, L2, there is also L1. So then that means there is you can do a tiling within tiling within tiling. Then that means you'll get a 12-way nested loop. And there are 3 parameters. Like for example, in the first case, we have only one tile size. but you have S1, S2, S3, and the performance, the performance of your matrix multiplication problem, if you call it as P, MM, S3, and also, yeah, the number of, let's ignore course. So what happens is deciding this S1, S2, S3, it becomes a challenge because it's not like a monotonically increasing thing. There's no properties for it. So everything becomes very difficult. Okay. So it's a multi-dimensional optimization problem now. Okay. And you can make it more complex because you can include in this parameter list the number of cores. Okay. And many other things, and all these things just makes the whole simple matrix multiplication problem humongously complex. Sorry? Because L3, L2, if you think of L3 and L2, if you do tiling within tiling, then you can use the number of L3 misses will be less. If you access L2 and if data is not present in L2, you go to L3, right? You want to reduce the number of L3 accesses. So good point. So let's say if you just take this only S style, okay? If you take S style, you may minimize the L3 main memory misses. But the number of L1 misses will be bad because primarily for the reason this data comes to L1. From L3 data keeps going to L1, it gets ejected out, and then again it keeps. Yeah, that's true. Even for L2, if you just look at L2, L3 interface also, that is true. No, that's why you want to minimize. Because data that you're optimizing, if you just work on S style, then you are reducing the number of main memory misses. But if you compare it with L2 and L3, there could be lots of L2 misses because it just keeps coming and going. Okay. Okay. So there is a lot of craziness happening here. Yeah. So, well, how do we solve this problem? Okay. Is there a way to solve this problem? And also there is another issue here. You use your choose S, let's say magically you do a lot of hard work and pick all these tile sizes. But when you actually run your program, there is other workload that is present on your system that will interfere with your problem, making your life much more worse. Okay. So effectively, at the time of benchmarking your program, you may have, let's say, 1 MB of cache available. But when it is co-located with something else, then the effective cache, instead of getting 1 MB, you may get only half MB. And because of that, the tile sizes that you have chosen, they could be bad for you. Yes or no? And this is one of the things that can cause a problem when you put our work on the cloud. Because let's say you deploy your workload, if you benchmark your program, that's a good exercise. On a same machine on cloud versus bare metal machine, is there any performance difference? Because on the cloud, your workload could be co-located with someone else's workload, and that could be heavily interfering with your cache performance. Okay. So now let's conclude this discussion in the last 5 minutes. I know you are tired, but there's a beautiful idea. From there, we'll conclude this. So this brings us to this final idea on cache oblivious algorithms. So now we didn't consider recursive matrix multiplication at all. Okay. So the matrix multiplication, it can be looked at like this. You can divide the matrix A times B. You can think of it as, A11 times B11 plus A12 times B21. So this is the recursive matrix multiplication. Okay. Well, you can write the same code in the form of a tiled loop also, where the tile size of the tile is half the size of the matrix, of course. But you can recurse. Okay, and then there is you also know Strassen's algorithm for matrix multiplication, where the time complexity is less than from n cube, it goes down to something. Okay, some. So now tell me, if you keep recursing like this, do you get any advantage on this recursive matrix multiplication when compared with the tiled version of matrix multiplication that we have seen just before? Yeah, this is parallelizable. Of course, it's one. Great. Yeah, so that's the most beautiful thing about this is the matrix sizes you're not doing, it keeps on, the problem sizes keeps on going down, 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 down. And finally, when it the leaf nodes, things start, cache misses start happening. And as you go up, the data is still already there. Okay. So because of that, you don't need to do any tiling. You don't need to optimize your code for L1, L2, L3 caches and main. And this whole thing automatically pans out well, takes care of the cache hierarchy. And even if the effective cache size goes down because of some other workload, you cannot do better than this recursive matrix multiplication uh, with any other, compared to any other problem. Okay. So this is what is called as a cache oblivious problem, cache oblivious way of uh, writing code, because when you are optimizing your code, you're not optimizing it for any specific cache. Okay. And if you see the analysis here, this is work analysis. It will be theta cube. That is when we move from loop version to recursive version, this work is still n cube. That's what is being shown here. But what is important here is, if you see, this is the analysis of cache misses. If you see, so the number of cache misses here is equal to 8 times, there are 8 sub-problems, multiplications and additions. And when the size of this n square falls below that cache line, then what you have here is this nice thing that then the number of cache misses will be n square. Okay. So what is the cool thing about this algorithm is, this is self-adaptive. We need this for analysis purpose only. But when you are executing the algorithm, we don't need this one. It doesn't matter what is the value of B. Yes or no? It automatically comes. We are using this condition only for analysis purpose. Okay. So what happens is, when you apply this recursive matrix multiplication, it's a cache oblivious algorithm. And it's cache oblivious, and it gives you excellent, it optimizes the number, it minimizes the number of main memory accesses. Not only main memory accesses, it minimizes the data transfer between L2, L3, it minimizes the data transfer between L1 and L2, and all the hierarchy is automatically taken care of. And what is the important thing here is, again, I would like to insist, if the effective cache size reduces from 8 MB to 6 MB, because there is another application which is competing with you for cache, the performance that you get out of this is still optimal given the circumstances. But on the contrary, if you fix the tile size, assuming that you have 8 MB cache, then the performance that you get, when you use a 6 MB cache, it will be suboptimal. Okay. So the whole story is brilliant. Where does this add up? No, if you can you write this recursive matrix multiplication code? It's just easy, right? You can do it in half an hour and compare it with your gem. Will it do better than your gem? Sorry? Yeah, there is a lot of overhead for recursion. Okay. So usually the way we try to avoid overhead for recursion is you have to stop recursion at some place. That will, the place where you stop the recursion defines your performance. And yeah, so at least what happens in that case is instead of tuning your algorithm for a instead of tuning multiple parameters, you can tune on one parameter, that is where you would like to stop your recursion. And where you would like to stop your recursion, ideally speaking, if you know this thing, then if n is less than cm, then what can you do is you can stop recursion there, right? Assuming if you are just optimizing for L3 and main memory accesses. Does this make sense? If you are just optimizing for L3 and main memory accesses, and as soon as you know that n is less than cm, then you can stop recursion, right? So that way you will save a lot of recursion overhead. You can do that. It's just that, it's just pain. Yeah, too complicated. And actually what you should do is you write recursive code and put silk spawn keyword and see what happens. Okay, I think you should try it. Okay, you just take matrix multiplication, you apply recursion, and you just put silk spawn there, and the threads are automatically generated. The number of cores that are there, the runtime system takes care of a lot of things, and you can see whether it beats your best gem performance. And if it beats your best gem performance, then this class is few days late for you. Okay, I'm sorry, so I'll taking for extra time. I'll stop here. But this area of